Hello and welcome. My name is Mr. Stabner, and this is another lesson in logarithms. In this fourth and final part, we're going to take a look at exponential growth and decay. So here are some common growth and decay formulas. The top formula deals primarily with calculating growth or decay at some portion of the year, or maybe just once a year. Two common ways to use this first formula are by calculating monthly growth or decay or yearly growth and decay. If it's monthly, you are calculating your growth or decay 12 times a year, so n would be 12. But if it's yearly, just once a year, then n would be 1, which the n's would then just simplify into the formula, and it would look like they weren't there at all. Now, the second formula is if growth or decay is calculated continuously. That means it just never stops growing or never stops decaying. So in that situation, we're not too concerned about how many times it is calculated. It just never stops growing. But since it's continuously growing, we're going to use E as our base. And finally, the third formula is a specific type of decay formula called the half-life formula. You might have seen this before if you have taken a chemistry class. Now, the last piece of business is the placement of the variables. Because to be perfectly honest with you, the variables will change depending on what textbook you open, depending what class you're in, even if you're working with science versus math. So focus more about the placement of where the variables are, less about the specific letters. So A in our case is the final amount. P is going to be the starting amount. T and R, those are pretty universal. T is for time, R is for rate. And if we're talking about specifically half-life, instead of R, we replace that with H, because half-life is specifically how long it takes an item to lose half its value. So what we have in this first scenario is yearly growth. Movie tickets are averaging $9.75 a ticket, but are increasing at 6% every year. So what we're able to do is set up an initial formula so that we can answer the two equations later. We don't know what any future value might be, but we do know that the initial value for these movie tickets is $9.75. And we have a 6% growth rate, so we're going to add that 0.06 on the inside, and we don't know how much time we're being asked in the general sense, so we're going to put t in for an exponent. So let's take a look at the two questions for this scenario. The first question asks, how much will the tickets cost 5 years from now? The second question asks, how many months will it take for the average movie ticket to cost $12? So if we want to know how much a future value is, we just need to input the time. So our future value is going to be 9.75 times 1.06 raised to the fifth power, which is going to be 13.0477. But we're not just going to leave our answer like that. We were asked how much, so we need to write it in proper units. So our answer is going to be $13.05. Now, if we're calculating a time frame for one value to approach another, we have to solve it a little bit differently. So taking into consideration that we're going to solve for months, we need to figure out first how many years it'll take. So we start with our final value of 12, our initial value of 9.75, 1.06, but now we have t as an unknown. So now we have something very similar to the equations we solved in the previous video. But we have a number in front of our base of 1.06. We need to divide that away, and then we can solve it using similar techniques from the previous video. So this is what we have. We now have a division fraction over on the left side, but that's no big deal. All we need to really do is take a logarithm to both sides, which will allow the t to move in front, and then we can finish our solving for there. So after simplifying and solving, we get about 3.56 years as our answer. But I remind you that we are not solving for years, we are solving for months. So, need to multiply by 12, and then we'll get our actual final answer, which is approximately 42.76 months. If you want to see more examples of fully worked out detailed solving of exponential equations, please review video number 3, where I go more in depth into solving. So here is another example that, for all intents and purposes, is basically the same exact example as example 1, with one major difference. Instead of growth, we have decay. So we're going to go through this example a little bit quicker, but I'm going to make sure you see the one major difference before we, well, hit the turbo button. In this example, a powerful computer is being purchased for $1,300, but it loses value at 15% every year. So the formula is going to be practically the same. We have a final value equaling initial value, but instead of adding the rate, we're going to subtract the rate. 1 minus 15%, or 0.15 to the t power. Other than that, the process is the same. If we want to know how much it'll be worth in 3 years, we have A equals 1,300 times 0.85 raised to the third power, which is approximately $798.36. And if we want to know how long it will take for the computer to be worth half its value, half of $1,300 is $650, so that is our final value, equals our initial value, times 0.85 to the t power. Which, going through the exact same process for solving as the previous example, we're going to divide both sides by 1,300. Then we're going to take a natural log to both sides, which allows us to move the exponent t to the front. And then after a little bit of division, we're able to get an approximate value for t, 4.265 years. Now, if you haven't already noticed a cool little thing, when you work with something losing half its original value, half will exist in your equation, which, that's right here. So in this third example, Mr. Stabner is investing $500, so that is our initial amount. However, we cannot just write 1 plus an interest rate. This time, the fixed annual interest rate of 8% is being compounded quarterly. It's being calculated 4 times a year. So instead of 1 plus our rate, it's 1 plus our rate divided by 4. And instead of an exponent of t, our exponent is 4t. So now this is the scenario that we are going to have to solve with. So if we were to check how long will it take for his money to double, 1,000 would be double of 500. And after we divide our rate by 4, we have 1.02 on the inside, but we still have 4t as our exponent. Now we just need to use the same solving process we did before. So after dividing the 500 into 1,000, we have 2 equals 1.02 raised to the 4t power, which after taking the natural logarithm of both sides, the 4t moves to the front, which then allows us to divide the 4 and the natural log of 1.02 over to the other side, which gives us an approximate value of 8.75 years. As far as figuring out how much the account will be worth in 15 years, that's no big deal. We're just going to substitute 15 in for t. So our exponent's going to end up being 60 because 4 times 15 is 60. But calculating that, we end up getting that the account would be worth approximately $1,640.52. So in this fourth example, we're examining bacterial growth, which always happens at a continuous rate. So we're going to have to use this equation. A equals PE to the RT. So in this scenario specifically, a scientist discovers that the 100 bacteria she started with 6 hours later ends up being 450 bacteria. And she wants to calculate what the growth constant is for this bacteria. What is that growth rate? So we start with the final amount of 450, initial amount of 100, E, and then we're going to have on top 6R. We're going to actually solve for R this time. But the rest is just solving. We start by dividing both sides by 100, as per usual. Now this allows us to take the natural log of both sides, which, using the power property, transforms the 6r from being an exponent into being a number in front, a coefficient. Now, as we discussed earlier, if the base and the log are the same, they're going to simplify out, they're going to cancel out to 1, so the ln and e basically just disappear. We can then divide by 6, which gives us a rate of approximately 25%, which is pretty high. Let me show you what I mean by that. In the second part, we're going to see what, under optimal conditions, the bacteria will do after 1 day. So we have A equals 100 times e to the rate we found in the previous problem, 0.2507, but instead of 6 hours, we're going a full 24, which would be approximately 41,026 bacteria. So think about it. After 1 day, 100 tiny little bacteria are now over 40,000 strong. That's how big a growth rate of 25% is. So to finish up, I'm going to quickly go through a half-life example. If you start with 30 grams of iodine-131, which has a half-life of 8 days, you can easily calculate how much would be left after 20 days, which is about 5.3 grams. But if I want to calculate how long it would take a 100-gram sample to reduce down to 10 grams, this is the formula I'm going to set up, which, by using the same techniques as before and doing a little bit of algebra, we'll get that it'll take about 26.58 days to have that sample go from 100 grams down to 10. So thank you for watching. I hope you learned a little bit more about solving exponential and growth formulas, and I hope you enjoyed this series overall. My name is Mr. Stabner. Have a wonderful day.